Hey there, and welcome to This Explainer. Today, we're cracking open what is literally the ultimate existential cold case. Seriously, just look around you for a second. The Earth, the stars, the very device you're watching this on right now, it's all made of matter. But here's the crazy part. According to the laws of physics, absolutely none of this should be here. Our universe should just be a vast, empty void of pure energy. So, why do we exist? Well, the answer might just lie with the most elusive, ghostly particle we've ever discovered.
Okay, let's dive right into this. To frame our entire investigation today, I want you to consider this idea. The ghostly neutrino? A particle so incredibly small and unreactive that scientists used to think it was completely massless, could be the singular reason you and I are actually here to ask these questions in the first place.
And that brings us to the central mystery of the Big Bang. You see, when the universe sprang into existence about 13.8 billion years ago, that immense heat and energy should have produced perfectly equal parts of matter and its twin, antimatter. But there is a massive problem with that perfect symmetry. If they were created completely equally, they should have completely annihilated each other in the blink of an eye.
Section 1. The missing antimatter mystery. A universe of pure energy? You know, what's actually wild is just how similar these two cosmic rivals really are. Matter, the familiar protons, neutrons, and electrons we all know, has a literal mirror counterpart. Antimatter is almost identical, but with its quantum charges flipped. So for example, a positron is essentially just an electron, but it's carrying a positive charge instead of a negative one. They are exact cosmic opposites.
But here's the massive catch. Whenever matter and antimatter actually meet, it is a profoundly destructive reunion. According to Einstein's famous equation E equals mc squared, they annihilate one another perfectly. They convert 100% of their mass into pure radiation. So the fact that our matter-filled universe somehow survived this initial cosmic battle royal, it's a glaring, massive anomaly.
Section 2. Rules of the imbalance. The crime scene conditions.
So back in 1967, physicist Andrei Sakharov laid out 3 really strict requirements the early universe had to meet to produce a matter surplus. You need baryon number violation, a departure from thermal equilibrium, and most importantly for our investigation today, you need C and CP violation. Okay, so the absolutely crucial one for us is that second condition, CP violation. Think of it kind of like a mirror image and charge flip rule. If you take a particle, flip its charge, and reflect its physical orientation like you're looking in a mirror, CP symmetry says it should behave exactly the same way. But what if it behaves slightly differently? Well, that is a violation. It basically means matter and antimatter aren't perfectly identical twins after all.
Now, we've actually seen CP violation happen in standard particles like quarks, but they've got an airtight alibi. The imbalance caused by the standard model of particle physics is literally millions of times too weak to explain the massive amount of matter in our universe. If quarks were the only culprits here, we still wouldn't exist. We need a new suspect.
Section 3. Enter the shape-shifting neutrino, the prime suspect.
Okay, so neutrinos. They're tiny, neutral, and notoriously antisocial. In fact, they're so ghostly that about 60 billion of them from our sun are passing through every single square centimeter of your skin right this very second. Crazy, right? You don't feel them at all because they interact so incredibly weakly with normal matter. For a long time, physicists thought they had absolutely zero mass.
But then, right in the late 1990s, experiments proved everyone wrong by discovering neutrino oscillation. As neutrinos travel through space, they have this bizarre quantum ability to shapeshift between 3 different flavors: electron, muon, and tau. And mathematically, the only way this shapeshifting is even possible is if neutrinos actually possess a tiny, tiny amount of mass. This discovery totally broke the standard model wide open.
Section 4. The cosmic seesaw mechanism, balancing the scales.
To figure this out, physicists came up with the Type 1 seesaw mechanism. I want you to imagine a literal playground seesaw. To balance out the incredibly light, everyday neutrinos that we actually observe, there has to be a counterpart sitting on the other side of that seesaw, an unseen, massively heavy, right-handed neutrino. And the rule is, the heavier the unseen giant gets, the lighter our observable neutrino becomes.
So on one side of this seesaw, you've got left-handed neutrinos, the extremely light standard ones we detect all the time. On the other side, you have these theoretical right-handed neutrinos. They are absolute giants, up to 10 to the 15th times heavier than a proton. But because they were so heavy and so unstable, they would have existed only for a fleeting fraction of a second right after the Big Bang before completely decaying.
Section 5. Leptogenesis creates the universe. The cosmic exchange rate.
So what exactly is leptogenesis? Well, it's this specific theoretical framework that says when those giant, heavy, right-handed neutrinos decayed, they didn't do it evenly. They actually violated that CP symmetry we talked about earlier. Their decay slightly favored the creation of leptons, which are particles like electrons and our lightweight neutrinos, over antileptons.
Here's the step-by-step breakdown. First, those heavy giants decay asymmetrically. Second, this leaves the universe with a surplus of normal leptons over antimatter leptons. And third, we get what's kind of like a cosmic exchange rate. At the extreme temperatures of the early universe, these quantum anomalies called sphelerons sweep in. Sphelerons act just like a currency exchange, taking that surplus of leptons and converting them into baryons, the heavy particles like protons and neutrons that make up all the matter we see today.
Now, theoretical whiteboard physics is awesome, but we need hard proof, right? Section 6. The Underground Hunt. Catching the ghosts in the act.
To prove the seesaw mechanism and leptogenesis are real, scientists basically need to catch the neutrino acting as its own antimatter. They're hunting for a super-rare event called neutrinoless double beta decay. In standard nuclear decay, neutrons emit electrons and neutrinos, but if neutrinos are their own antiparticles, they could theoretically just annihilate each other inside the nucleus during the decay, leaving exactly 0 neutrinos behind.
And let me tell you, there's a massive international engineering effort going on right now to find this. Deep underground, to shield everything from cosmic rays, scientists are building giant vats of exotic radioactive isotopes. We've got the Comland Zen experiment in Japan using xenon-136, the EXO and NEXO projects in North America, and the Jurda and Legend experiments over in Europe using germanium-76.
And honestly, that's not all. We're also trying to measure neutrino CP violation directly with the Dune experiment. They're going to literally shoot a beam of neutrinos and antineutrinos through 800 miles of solid bedrock, straight from Fermilab near Chicago all the way to a massive underground detector in South Dakota. They want to see if the neutrinos and antineutrinos shape-shift differently on that journey.
The sheer precision of these experiments is it's mind-boggling. By searching for neutrinoless double beta decay, these underground detectors have successfully ruled out half-lives of up to 10 to the 26th power years. That is quadrillions of times older than the age of the universe itself. They are pushing the absolute limits of physics, basically just waiting for a single atomic nucleus to reveal the universe's greatest secret.
And that brings us to one final, staggering thought to take away from this explainer today. If these experiments eventually prove that neutrinos truly are their own antiparticles and that they violate the universe's most fundamental symmetries, does that mean the vast, sprawling cosmos we live in survived total annihilation simply because a nearly massless ghost particle decided to change its shape at the dawn of time? It's a mystery that scientists are closer than ever to finally solving. Thanks so much for joining me on this deep dive.